So let's start with some revision. So when we're talking about mutual induction, what is mutual induction? You've hit into an interesting topic, but no, so that's what we call self-induction, when a conductor inducts into itself, or coil does. So mutual induction. Yep, that's pretty close. Passes to another coil like transformer. Yep, that's a good one, Andy. Okay, just we're doing the revision. There is one activity sheet that goes along with today's lesson, and I've just posted that link. Yep, it's just conductor to conductor. So basically, so mutual induction is when a changing current in one coil induces a voltage into another nearby coil. This principle is used in devices like transformers or motors, where energy is transferred between coils without direct electrical contact. So we use a lot of things that use mutual or mutual induction. So the basic one is your transformer, which we use to step up and step down voltages, or motors. Motors use interacting magnetic fields. By a magnetic field is taken from the outside to the rotor, which is the bit that spins, which you guys will learn about next year. But just a heads up, you will be revisiting topics of magnetism next year. Can anyone think of anything else we might do with the transformer just while we're talking about it? So we've got our step up and step down. What other kind of transformers do you guys know about? Okay, that would be a rectifier. Yep, isolating transformer. Yep, that's a good one. Induced voltage in nearby circuits. Yep. Not sure where that would be used, but possibility. But yeah, we just need to be aware of these ideas of magnetism because they do play a part, especially when it comes to everyday things like transformers. Like there are small transformers inside the power packs for your laptops or inside the devices you use to charge your phone. So if you think about that USB port in the PowerPoints, there's a little tiny transformer in there that changes it, steps down the voltage before it changes it to DC. Yep, current transformers, yep, or CTs, which we use for monitoring power usage or current usage. Yep, good answers, guys. Cool. So how does an electromagnet work inside of a relay? So a buck converter is more changing a DC level of voltage. That's considered a switch mode power supply. All good, Ryan. We're just doing some revision. So yeah, so what does an electromagnetic work? How does it work in a relay? So yeah, we've got a coil. What does that coil do? Yep. Yep, good. It's a good answer, guys. So yeah, so when current flows through a coil of the relay, it creates a magnetic field that pulls an armature. Closing or opening contacts control another circuit. The coil essentially acts as an electromagnet that moves a mechanical switch. So with relays, you're normally switching lower currents, so generally up to maybe 10 amps, and you're normally changing. It's more like a light switch, a two-position light switch. So you've got your common, your 1, and your 2. So it switches the common between 1 and 2, whereas your contactor, which controls bigger current, is normally a closing. So it doesn't so much switch as it closes a contact or opens a contact. It is still a switch, but your relay is more designed for your low current draw, so your lighting circuits or controlling low current machinery. Your contactor is more for your motors, your big grunty circuits. Cool. So what's the difference between self and mutual induction? We kind of already touched on it a little bit. All good, Blake. Just try and post as many messages in response to questions as you can from now on, but all good. So Timothy's explanation is pretty succinct. It's good. So self-induction occurs when a change in current in a coil induces a voltage in the same coil. This opposes the change in current, or Lenz's law. Mutual induction, on another hand, involves two separate coils. One change in current induces a voltage in the other. So when we use coils, there's always going to be a little bit of self-induction that opposes current flow. And this is dangerous because what happens is the magnetic field builds up inside the coil, and then when we turn the power off, the field collapses, but it causes a back EMF into in the opposite direction. So even if we turn it off straight away, it could have a little bit of EMF left in the windings. So something we need to be aware of when we're working with coils and magnetic fields. Cool. So AC versus DC principles and AC waveforms. So tonight we're going to have a look at AC and DC currents and voltages and look at the difference in generation and the way we use them. Cool. So starting off with some AC versus DC. So here is a helpful table so we can look at. So when we look at the aspects of flow direction, direct current, because it's directional, it only flows in one direction. An AC or alternating current, it constantly reverses direction back and forth. Voltage polarity, so with direct current, you get a constant voltage. But with AC, it alternates between the positive and negative polarity, even though when we use our meters, and I'll talk about that in a little bit, we only see a constant voltage on AC. Sometimes it maybe fluctuates 0.1 of a volt sometimes. So your sources for DC, you've got your batteries, your solar panels. So we get AC from the inverter, but the solar panels themselves put out DC and DC power supplies. Whereas AC we get from generators, main supply, and alternators. So the graph shape, so direct current is just a flat line, steady voltage on a graph. And AC current and is a sine wave, periodic oscillation, and we'll have a look at that in a little bit. Frequency, generally you get 0 hertz with DC because there's no reversal, there's no back and forth. And 50 hertz in New Zealand reverses 50 times a second. So we'll also talk a little bit about that when we get to the sine wave. So common uses for your DC, electronics, your car systems, small portable devices, your electric cars, and then AC we use for household power, industrial machinery, and general power distribution. Cool. So where in our day-to-day lives do we use DC power? Or where do you in your daily life use DC power? Yep, power tools, I like that one. Yeah, so just keep checking them out there, guys. Everyone uses DC somewhere. Laptop chargers. So your laptop chargers in DC. You can't stick an AC socket to it. Yeah, remote controls, flashlights. Yeah. Cool. So these are the places we use DC. Where is AC used? So think about where it's AC, but it doesn't get changed into DC. Yeah, we look at the example of the lighting in the house. Well, it uses AC power, but up until the lights, if it's an LED, it uses DC. Yeah, your oven, your dryer, your washing machine, yeah, they all use AC. Yeah, pumps. Yeah, your heaters, AC, your air conditioning. I don't know if any of you guys have like a breakfast smoothie in the morning that uses AC power. People like to do baking. Your stand mixers, they use AC, and they've got motors in them. So you'll learn about next year about the way the frequency affects the motor. Toaster. Toaster's a good one. It's a decent resistive load. So if you use a kettle in the morning to have coffee or tea, or you use a coffee machine, all kinds of things that use AC power. Yeah, jug. Yeah, hot water cylinder is a good one. Hopefully this works. Yep, fan. Yeah. Cool. So basic explanation of AC versus DC. So just on the topic of high voltage DC, can anyone tell me where we have that in New Zealand? Yeah, Haywoods to Benmore. So you learn about this. Yes, it comes up in year 2. You start talking about the HVDC link. It runs from Benmore in the South Island up through to Fighting Bay. Oh, good, Antonio. So from Benmore Power Station to Fighting Bay overland, where it ducks under the Cook Strait from Fighting Bay to Offero Bay here in the North Island, just outside Wellington, then goes overland up past Macra and then over to the Hayward substation. So back when they first built it in 1965, Health and safety was a lot less. Most of the power was generated in the South Island with mass hydro and used a lot more in the North Island because that's where the populace was. But now it's kind of back and forth because we're generating more solar, which is already DC based here, and we're transmitting that to the South Island so the hydro power plants can store more water in their dams for nighttime usage. And it's of particular importance now because they are looking at replacing the HVDC link underwater cables, probably by, I think they said 2035, at an estimated cost of $1.4 billion. So there's going to be a fair bit of work for some people. I think there's Prismian, some company overseas, to come and install the cables. But yeah, so a lot of stuff happening in the network stuff in the near future, hopefully. Cool. So DC generation. So yeah, so you can see the DC. So we've got a few different parts of the DC alternator here. So hopefully you can see it, but we've got two rings there. And basically, as the coil rotates inside the magnetic field, those rings switch which side of the coil is connected to which conductor. So that way the current is only, or the voltage is only ever going one way. It's a form of commutator. So this ensures that if we're generating in DC, we only get DC instead of AC. So that is a very basic one-loop DC generator. But then if we look at the actual generator waveform, we can see that it is not actually a flat line, it's humped. So we get lumpy or pulsating DC from a DC generator. Any questions about this so far? So one of the things I got taught or learned while I was away in Auckland doing that course is the only ever dumb question is the one you don't ask. So if you've got any questions, it may seem a bit silly, might be a little bit side of the topic, just ask. I'd rather you guys ask, me answer it, and we leave it at that. So pulsating DC. So if we look at the waveform being generated here, as the coil, so it comes to 90 degrees with the field, and then it comes down to 180. So basically it lumps it's lumping DC. Yeah, so the reason it's lumpy DC instead of AC is because of those commutator rings that I was talking about. So as the coil switches sides, it keeps the direction that so we'll go back. So you see here in the animation, if you look closely at those rings, they're actually two split rings. What's the best way? So I think the best way to, yeah, it doesn't go to negative because the conductor switches side. So let me get a pen, one of these digital pens, and I'll draw it. So if we look at those two commutator rings that we were talking about just before, so this is a 1D. So we've got a connection point here and a connection point here. So this is our negative and this is our positive. Right now the coil, we'll call this the coil, is flat. Probably more likely. So as this spins, say the coil gets to about here, the commutator rings will be like this, but the connection will be here. So as it then comes and rotates again, it'll change. So this commutator will become to the positive. This segment will come to the negative. So instead of generating the AC, it will armature. Yeah, armature, that's a good one. So instead of generating AC, it generates lumpy DC or pulsating DC. So again, that's the most basic type of generator and generates pulsating DC. So simple DC generator is very similar to a simple AC alternator. So there is still a magnetic field and there's still a loop of wire that rotates within the magnetic field. The key difference is how it's connected to the external circuit. In a simple generator, the slip rings have been removed and replaced with what is called a commutator. So that's what those two segments are. So the purpose of this construction is to create a pulsating direct current rather than sine wave alternating current. During the first half of the rotation that loop does, the waveform is identical to the alternator sine wave. But once the rotation reaches the 0 point, connection is lost, and as if the rotation starts again. So this leads to two positive cycles each time that the loop rotates 360 degrees within the magnetic field. So that's how a DC generator works. Cool. So the basic commutator looks a little bit like this. This is a better picture. So like a slip ring, so the only one ring and the ring is split in half. Each half is then connected to the loop of wire and is rotating within the magnetic field. Brushes are then held against the commutator to draw the current away to the external circuit. You can see there the two halves of the slip ring. As they change halves, they become the opposite. So as they swap over, one becomes positive, one becomes negative, but the coil keeps rotating. But then once we have DC, we need to smooth it out. So in order to do this, to get a steady ripple-free direct current, we can add to the simple generator by adding more loops and more segments to the commutator. There are still only two brushes and they are in contact with whichever commutator segment is generating the most EMF at any one time. It means that each loop peaks at a slightly different time and the brushes are connected to the peak, thus creating a wave that gently pulses across the tops of the waveform and doesn't seemingly crash up and down like a single loop version. And then once we have this slightly smooth or ripple DC, or ripple free, we can then smooth it out even more using other electronic devices, which you guys will learn about next year, things like capacitors. Cool. So any more questions about DC generation? Anything you want me to go back over? No, so solar is the only constant DC that we do you generate. So in New Zealand, 90% or like 80% of our generation is done through moving or rotating machines. Solar is the only one that doesn't use rotational energy, and it's the only one that generates a pure DC signal. No, with the solar, we actually have to use an inverter to change it back to AC. Yeah, I don't know too many places where they do use DC generators, but I do know that we need to know about it for our studies, and it most likely will come up in the capstone. So just remind everyone, we do have a capstone at the end of the term. So we're in week 3, so we've got about 5 more weeks of study, and then we will be into the capstone. So if I open up the Learning Hive, I can show you the calendar. If you guys aren't familiar with it, it does outline all the stuff we go over. There are two options. Actually, sorry, there are three options with the capstone. If you come within 5% of a pass mark, the LSM, whoever your LSM is, I believe Mark, sits down with you and has a verbal chat. And then basically, if you satisfy him that you do know your stuff, he'll bump your mark up to a pass. Any more than 5%, basically they'll look at either doing a reset or the next time we do a capstone. But it's based on everything we've done this year, and you guys have done well enough to pass. I believe pass level is 60%. It is online, so it'll be just like your end of term exams or tests, sorry. So this is the calendar, and then if we zoom in, we come over here to the last term. So currently it is the 13th, so we're in week 3. So 4, 5 is going to be magnetism and generation. 6, 7, 8 a capstone prep, and then capstone on the 24th. So yeah, it is an online assessment. Just like you've been doing your exams at the end of each term, you'll be given a password. You'll get a certain time to do it. It'll be 100 questions based on the topics that we have done this year. But yeah, basically, you have to pass the capstone to get into year 2. And then after that, you have the capstone at the end of year 2. And then after that, year 3, you have your national exams. That's how it works. Cool. So we'll move on to AC generation. Cool. So when we talk about AC generation, we need to start talking about sinusoidal waveforms or sine waves. Cool. So we've already seen that when a length of conductor wire is moved at an angle through a magnetic field, the induced EMF is proportional to the sine of that angle. So when a loop of conductor wire is rotated in an anti-clockwise direction in a magnetic field, it passes through all angles from 0 to 360. Because the angle keeps changing, the induced EMF keeps changing. But in any particular instance, it is always proportional to the sine of the angle which the conductor is making to the horizontal at that instant. And always remember, we need motion in order for EMF to be induced. As soon as we stop moving the conductor, EMF stops being generated. Cool. We plot a graph illustrating how the sine of an angle changes as the angle is changed from 0 through to 360. The shape of the graph is the same as the shape of the EMF induced in the loop as it rotates through one revolution. So the angle at any instant is plotted on the horizontal axis, and the sine of the angle at that instant is plotted on the vertical axis. In theory, we should use every angle and every sine, but we can make a good approximation if we use every 10 degrees. So if we start with the angle, we can start figuring out the sine of it. So we'll do the first one. Sine of angle 0 is 0. All right, get out your calculators, and we'll do this quick. Can you guys give me the sine of the sine of angle 10? Just got the calculator. Yep. Cool. So yeah, 0.174 according to the PowerPoint. Cool. What about 20? Yeah, 342. Yeah. So you guys are getting it? Cool. So I'll do the next few. So as we get to 30, 0.5, 0.643, 7.766, 0.866, 0.94. What about 80? Just put into your calculator sine of the angle. So put sine 80. So it's not necessarily a formula. We're just looking at what the sine of the angle would be. It gives us a decimal approximation of the sine wave, or a percentage of the sine wave. Yep, 0.985 or 984. And then sine of 90 is 1. And then if we go back, or we start going to 100, 110, we start seeing a familiar pattern. 0.985, 94, 866, 766. So as we get closer to the end, so, yep. So as we get to angle, so as we get to 0 and 180, we are on 0. So everything in between is a reflection of itself. So a sine wave is pretty much if you were to split it at 90 degrees, the sine waves would be identical on both sides. So what about sine 190? Yeah, so as we start to get down towards the second half of the sine wave, because it is a sine wave, we are moving into the negative value. So it is the same as 10, but it is now negative. So as we go down, it's the same, but we are now in the negative. So as we get to 270, we get to -1. So we have done we've gotten to the peak of the negative sine wave at -1. And then as we come back down the other side of the sine wave, it's a reversal of what we were just doing, all the way back to -0. So we can see the two positive sides of the sine wave, from 0 to 180, and then from 180 to 360, we see the negative side of the sine wave. And this is what that sine wave then looks like. So how many of you guys have seen this before? Cool. And how many of you guys are getting flashbacks to high school physics and calculus? Yeah. Having a chat with one of the guys who are on the assessor team who used to be a tutor, and he said doing electrical theory is basically doing the real physics and maths of the real world. So although we talk in the theoretical at night class, this is the stuff you deal with every day. If you work with AC, you deal with sine waves. So now we'll look at the properties of a sinusoidal or sine wave. So if you examine the sine wave, you will see that it starts at 0 and rises to a positive maximum value before falling to 0 again. So it then rises the opposite direction to a negative maximum value equal to the positive before falling to 0 again. So these maximum values, or maxima, correspond to 90 and 270 degrees respectively, because sine 90 is 1, and as we looked at before, sine 270 is -1. That's all good, Jack. As long as you try and post as often as you can responses, and then if you miss anything, just jump in on the video. I will probably edit out the videos that I will show tonight, just so that the video doesn't get taken down off YouTube. Cool. So therefore, the equation EMF BLV sine theta can be reduced to BLV when theta is 90 degrees. But you probably won't have to do that calculation a little bit. Cool. So this EMF is the maximum possible for any particular combination of magnetic field, conductor, length, and rotational velocity, and is normally abbreviated to E. That's fine as long as they're there and I can look them up when I do the roster. That's the main thing. Is that yeah, if I can justify marking you present, even though some people look at it and go, well, they didn't have the camera on. Well, they were putting messages in the chat, so they were here. So similar, the equation reduces to EMF equals BLV -1 when theta is 270. This negative maximum is likely to abbreviate to -E. However, as we know, that negative maximum is equal to the positive maximum, so there's really no need to calculate it separately. Cool. So you will be asked about these kind of questions. So the maximum, yes. And a lot of calculations you will see instead of voltage, they use, or EMF, they use E. Yeah, so you will see sometimes in your formulas that you get given, instead of voltage, they use the letter E. Cool. So as I was saying, yeah, maximum value is known as the peak value. So voltage peak, which is from 0 to the top of the sine wave. The value between the positive and negative peaks is known as the peak to peak value, P to P. And for a sine wave, this is always twice the peak value. So some examples. A conductor loop of effective length 184 centimeters cuts a magnetic field of flux density to 527 milliteslas while rotating at 2.5 milliseconds. So we'll calculate the peak value of EMF induced into the loop and the resulting peak-to-peak value of the EMF. So remember, E equals BLV sine theta. So we ignore the sine theta when we're looking at 90 degrees. So E equals BLV when theta equals 90 degrees. So we're looking at the peak. So that's why we're just ignoring sine theta and going straight to BLV. So remember, B is the field strength and measured in milliteslas. So we need to convert that to teslas. The length is in centimeters. So we'll. Good question. So we know it's at 90 degrees because they're asking us to calculate the peak value of EMF. So if we're looking purely at the peak value of the loop, then we're looking, that's why we're at 90 degrees. And it's saying the effective length because that's the length that we're actually worried about when it's passing through the magnetic field. So it's not the actual, so BLV is the calculation we use to figure out the EMF induced into a length of wire or a conductor, and B is the flux density measured in normally teslas, but right now it's measured in milliteslas, so we need to convert it to teslas by dividing it by 1,000. L is the length of the conductor, which is 184 teslas length volts. Good one, Timothy. So 184 centimeters, which we need to convert into meters because that's the unit we normally use for calculations. And then velocity is measured in meters per second. So we don't need to change that because it's already in 2.5 meters per second. So we multiply those three values together and that gives us our effective EMF that's induced or our maximum EMF that's induced. Yeah, has anyone else got an answer? Okay, cool. Yep, so we start with our 527 milliteslas, which it says here times 10 to the -3, which is the same as dividing something by 1,000. Then we've got 184 times 10 to the -2, which is the same as dividing something by 100. And then times 2.5 meters per second, which gives us 2.4242 volts, or volt peak, which we would then round to 2.42, as all of you guys have. But now we need to figure out peak to peak. How do you think we would do this? Yeah, pretty much. We multiply it by a factor of 2 because if the peak is 2.42, then the peak must be double that, peak to peak. Cool. So the peak to peak voltage is 4.8484, which we would round to 4.85. Is that making sense? Anything anyone's unsure about? Yes, the exams will have a formula sheet. Yeah, so it's a sneaky question, but as long as we know that they're asking for the peak value, we know that the peak of the sine wave is 90 degrees. So as long as you guys remember that the sine wave is at its highest or its peak value at 90 degrees, because if we look at the sine wave, who posted that thing in the chat last time? The sine wave, if we look at a wheel as it goes around, they may ask for the negative peak, but it's the same formula except it goes into negative voltage. But we don't actually look at negative voltage, but yeah. If they ask you for the negative peak, then all you're doing is the same formula because it's just the sine of multiplied by -1. Yep, there we go. Thanks, Timothy. If we look at that wheel as it goes around, and then it relates to the sine wave. See, as we get to 180, we're at 0. Peak at 270, back to 0, nothing. So yeah. I don't think we would call it a negative voltage because it's AC, because we don't have negative voltages in AC. We go back a few pages. Yeah, we would look at it as a negative E. Yeah, you can't get a negative angle. Cool. So cycle and frequency. So each complete revolution of the conductor loop in the magnetic field induces one complete sine wave of voltage. One revolution is called one cycle or period. And the number of revolutions or cycles in 1 second is called the frequency. So the number of times it revolves around is the frequency. So the amount of times it goes up, the current flow goes up, voltage goes up and then down. Is called, how many times it does that is the frequency. So frequency is measured in cycles per second, or C per S. However, the term cycle per second is seldom used, is usually replaced by the word hertz, abbreviated to HZ. So if we think about 50 hertz in New Zealand, that's 50 cycles. So it's going positive and negative 50 times. So the voltage is actually, or voltage and current are changing directions 100 times per second. But we don't think about that change. We just think about one complete sine wave, and that's how we get 50 hertz. The frequency of electrical main supply in Great Britain is 50 hertz. To generate this frequency, power station generators have to rotate 3,000 revolutions per minute. As the main frequency is, or 50 Cs, 50 hertz or 50 Cs, it follows that each cycle or period must take 1/50th of a second to complete. The time for one cycle is called the cyclic or periodic time, so cyclical rate or periodic time, and it is defined as the reciprocal of frequency. So T equals 1 over F, F equals 1 over T. Does that make sense to everyone? So we think about 3,000 RPM. So we divide 3,000 by 60 to get seconds. So it's spinning 50 times a second. Cool. The frequency of a supply F is 50 hertz. Calculate T. So T equals 1 over F, which equals 1 divided by 50, or 0.02 seconds, or 20 milliseconds. So the frequency is changing every, so yeah, the sine wave, we're getting one sine wave every 20 milliseconds. Cool. So this is what the AC sine wave generation looks like versus the DC that we looked at earlier. The same principle, we're just now getting AC waveform instead of DC. Cool. So that's instead of making the horizontal axis in angles, degrees, it could equally have been measured in time, seconds. So for one cycle of main frequency, 90 degrees corresponds to 5 milliseconds, 180 to 10, 270 to 15, and of course 360 to 20 milliseconds. So if we replace the angles with time, this is what we would get. Cool. Any questions on that? Okay, cool. So instantaneous voltage. So the EMF induced at any particular point in the cycle is called an instantaneous voltage. So we've seen that EMF is induced at 90 degrees or 270 degrees is a maximum and is abbreviated to E. It follows that a voltage induced at any other angle or instant must be less than maximum. And so the abbreviation is changed to a small e. So E, big E equals BLV, and small e equals BLV sine theta. Therefore, E equals E times sine of theta. So if we have the maximum voltage, we can then multiply that by sine theta, or sine of the angle, to figure out the instantaneous voltage. So let's put it into practice. So the mains voltage has a frequency of 50 hertz and a peak value of 339.411 volts approximately. Calculate the instantaneous voltage E after 4 milliseconds and 19 milliseconds. This one might be a bit more difficult. So round up your answer to 3 decimal places. So T equals 1 over F, which equals 1 over 50, which is 20 milliseconds. So periodic time of the mains frequency, 50 hertz, is 20 milliseconds. So 20 milliseconds is the equivalent of 360 degrees. Cool. So, hey, therefore 1 millisecond is the equivalent of 360 divided by 20, which gives 18 degrees. So 4 milliseconds is the equivalent of 18 degrees times 4, which equals 72 degrees. Is this making sense? I don't want to get too far into this. Yeah, cool. Sweet, we'll go back. So what they're asking us here is to figure out the instantaneous voltage after the time. And so we know that 20 milliseconds is the time taken for one complete sine wave. So what we can do is take that 360 degrees and divide it by 20 milliseconds so that we know after every millisecond how many degrees it's gone through. So if we take the 4 milliseconds, we can take that 360 divided by 20, which gives us 18, and multiply it by 4, giving us 72. So yeah, instead of giving us an angle, they've given us a time period. So we know because we've got the frequency. So if they were to change that frequency to 60, we could also still figure out the time constant or the time taken to do the sine wave. So if they were to change the frequency to 60 hertz, 1 divided by 60 would give us 0.0166 or 16.7 milliseconds. Yeah, so now that we know how long it takes to complete one cycle, so the time period is 1 divided by frequency, 1 divided by 50, 20 milliseconds. So we can take 360 and chop that up into 1 millisecond pieces, which gives us 18 degrees. So we can then take our 18 degrees and multiply it by 4 milliseconds, which gives us 72. And then because we know E equals E sine theta, we know our angle is 72 degrees. So we can take our E equals big E times sine theta. And so 339.411 sine 72, which is based off of the previous slide. Peak value of 339.411 volts. And then we can times that by sine of 72 degrees. So what is the value EMF after 4 milliseconds? Have a go at putting that into your calculator. So what this question is getting us to do is take our knowledge of the fact that we know the one sine wave takes is 360 degrees, and we know we've got a frequency of 50 hertz. We can figure out the time period using that 50 hertz, and then we can divide our 360 degrees into 1 millisecond time periods. So yeah, it gives us a instantaneous voltage of 322.799 volts. Because if we were to round that up, it would end with 0.8. So this is where they would be on the sine wave. Cool. So because we know, now I can figure out what 1 millisecond is. what would be the angle of 19 milliseconds? That was the other part of the question, was 19 milliseconds. So you guys agree with? Yep, so yeah, 19 milliseconds is equivalent to 18 degrees times 19, which gives us 342 degrees. Cool, so we know E is equal to E sine theta. Our maximum voltage is 339.411. What is our voltage? Yep, so we take our 339.411 sine of 342, which gives us our negative 104.88 volts. So we would put that onto the sine wave. Yeah, we could round it up to 0.9. So that's where we would plot it on the sine wave graph. Cool. So before I move on to the next little part of the subject we're going to be doing, anyone got any issues or questions with this? Yeah, it does, because it knows that sine of that angle is a negative value because it is below the zero line. No. Okay. I'm trying to figure out how to go to. All right, let's see if I can do this. Here we go. Haha. I knew I could do this. So basically, when we're dealing with time, so the first thing we start off with is 50 hertz. Cool. So 50 hertz is our frequency. What this means is that 50 times a second, we have an alternation of the sine wave, so it completes one full cycle. So this is not the actual time taken to complete one sine wave. To figure that out, our time period is equal to 1 over this frequency. Basically, what we're doing is we're taking that 1 second and dividing it by how many times the sine wave gets repeated. So that would give us 1 over 50. So because we're dividing 1 second by how many times a second, so basically we're just reverting it back into one. This calculation gives us how many seconds it takes for it to do one cycle. So one full cycle like this. Okay, it erased it somehow. Cool. So we know that that will give us 0.2. Sorry, one too many zeros. 0.02, which is equivalent to 20 milliseconds. Cool. So now that we know it takes 20 milliseconds for one full cycle, we can take our 360 degrees and divide it by 20 to figure out how many degrees per millisecond are covered. So this would give us 18 degrees per millisecond. Is that making a bit more sense, Daniel? Sweet, cool. So now that we know we've got 18 degrees per millisecond, if it asks us for, cool, so actually, yeah, what is the voltage after 6 milliseconds? So what's the angle after 6 milliseconds? Sorry, guys. So we do 18 times 6. What do we get? 108. Cool. So we can then take, so E is equal to E sine 108. Cool. And if our E max is 325 volts, E is equal to what? Yeah, so with those results, I would be happy with 309.09 volts. Okay, so we've gone to 2 decimal places. I'd be happy with that, just because it gives us a little bit more accuracy. So in general, when you're doing your calculations and your tests, unless they say otherwise, put it to 2 decimal places. If they say you're wrong, challenge it. All it took me was one trip to Auckland to get the hang of using these smart whiteboards. Cool. So now the next part of the topic, we're going to look at root mean squared. So peak-to-peak values of voltage and current indicate only the maximum value the voltage has reached. To find an effective value, the root of the mean of the square is calculated since an average would be 0. The wave is equal, positive, and negative. So what do you guys think root mean squares mean? Means maths. Yes. Cool. So what it means? So basically, if we have our sine wave and we took a bunch of values from here, 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 basically every 10 degrees, and we added them up, we'd only get a whole bunch of this. So what we did is we took, so all values from every 10 degrees, what we did was we took all those values, so 10, 20, 30, 40, 50, etc. So what they had to do was they had to take all of these values and then, root of the mean of the square. So what we first did was we took all of these values, squared them, and added them together. Oh, sorry, no, we didn't add them together. So once the values were squared, we took the mean. Does everyone remember what the mean is when we talk about statistics? Yeah. So it's similar. So it's the average of a data sheet calculated by summing all the values and dividing them by the number of values. So what happens to a negative value when you square it? Yeah, it becomes positive. So what that did is gave us something. So we did then add them all together. And then we divided it by what? If we're taking every 10 degrees, how many times would we divide it? Yeah. 36 degrees, yeah. Or actually, would it be, because we're forgetting about 0. Mind you, 0 and 360 are basically the same. So we will call it 36. I'm pretty sure that's what they did. Then what we did after that, so when we talk about root mean squared, yeah, then we took all of this, square rooted it. So if you think about the way we do the same thing with, we add square values and then square root it and we get a higher value than if we just added them together for hypotenuse, similar thing. So this is basically what we did to get a value for an actual readable value. So in New Zealand, we have, most of the time we have an RMS voltage of 230 single phase. So that is an RMS value. And then our actual peak is normally about 325 volts. When you think about, no, it's only 230 volts. Yeah, that's the RMS value, but the actual peak voltage is 325. And then for 400 volts, it's slightly different. I can't remember that number off the top of my head. I only remember the 230 one because I mostly work domestic. So the RMS value is the voltage which a battery would need to generate the same power in a load. In other words, the size of the alternating voltage that can be quoted as an equivalent direct voltage. The RMS value is one most commonly used. So if a voltage is quoted without a suffix, it is assumed to be the RMS value. So RMS value is the one that we use. It's the one that our multimeters read. So whenever you stick your probes in and you get 230 volts, your meter is doing all of those calculations for you. Cool. So for a sine wave, the RMS value is found to be 0.707, 1 divided by square 2 times the peak value. So ERMS is equal to 0.707 of E max. So if we did that in reverse, we took our RMS value of 230 and we divide it by 0.707, we get 325.31824, etc., etc. So about 325 volts. And if we do the same for our 400 volts, we divide it by 0.707, we get 565.770, etc. volts. So it is kind of stuff we do need to know because it does affect the way we work in the electrical industry. Cool. So the RMS value is known and it is required to find the peak value. Then we divide the RMS value by 0.707. This is the same as multiplying the reciprocal of 0.707, which is 1.414 approximately. Don't worry about that. Just remember RMS 0.707. That's all you need to remember. So for the mains voltage, this means that the peak value is 230 multiplied by 1.414 or divided by 0.707, which gives us 325.3 volts. So it means that mains voltage of 230 they all pretty much read RMS. They'll say true RMS. I think they're just slightly more accurate than your average meter. But most multimeters will read RMS values because if they didn't, they'd just be constantly changing. I mean, if you look back at analog voltmeters, they still read RMS values. So, yeah, so 230 volt goes as high as 325.3 volts, extremely high and dangerous level, quite capable of causing death by electric shock. Always treat the mains with caution and follow all safety instructions when working with live equipment. On that note, do you guys know what your company's policy is regarding electric shocks? Don't get electric shocks? I like it. I like it. But in the event that an electric shock does occur, do you guys know what the procedure is for your company? Yeah, hospital, get it checked, safety observation. Yeah, so yeah, basically, general rule of thumb, even if your company's policy isn't this, you should be going to get a ECG or an echocardiogram at a hospital. Why? Can someone guess, give me a reason why we need to go get an ECG? You guys all have TLC, so assume you've done first aid. Yeah. Yep. Arterial. So it's ventricular fibrillation. Arterial. So when we talk about ventricular, it is talking about anything to do with the heart. The ventricles are the things that the chambers that your heart squeezes to pump blood through. So you have your left and right ventricle, and you have your left and right atrium. Yeah, so basically you're going to hospital to get an ECG. You're going to be there for between 2 to 4 hours. And yeah, they're going to check that your heart's going in the right rhythm. On the elite course that I was teaching in Auckland, they were asking, how bad of a shock does it have to be for you to go to hospital? Simple answer is, if you feel it, go. Doesn't matter. If the smallest little thing can throw your heart out of whack. So it's like, hey, if you feel it, you're going. They were ECHO apprentices. It's an ECHO policy. Most companies have the same policy. My previous employer did, and it was just a hard, fast rule. Shock, hospital, there for 2 hours, 4 hours, however long it takes for the doctor to say, yep, cool, you're fine. But again, yeah, because stuff's up your heart, you might not notice until you might not ever notice. You might feel a little bit poorly, just think you're sick, especially in wintertime, and then don't wake up. Just go to bed, don't wake up. All right. Sorry to get all down in the dumps, but it's been a very safety-focused kind of day. We've had some issues that in the company that we've had to deal with. Don't worry about it. Nothing to do with Wellington, but still. Cool. So now average voltage. So we figured out the roots mean squared. Now what about the average? So the V average is equal to 2 divided by pi. So 2 divided by 3.142, which gives us 0.637 volts. So obviously we would then multiply that by the peak voltage to give us average voltage. But we don't really need to know too much about average voltage. We're more concerned with RMS. Cool. And yeah, here's just a little fun animation of what a simple generator might look like. So if you notice there, instead of those 2 half rings, we have here what are called slip rings. So every time the loop completes 1 half revolution, it does not disconnect from the lead, and so it will alternate the current flow.